Good morning, ladies and gentlemen. Hope you're well today. It's a bit chilly here in North Carolina, and today we are going to be talking about OpenSSL. Now, OpenSSL is a pretty popular library for cryptography, and, well, it has a lot of tools, as we will see today. And today we're going to be talking about how it works, well, parts of it anyway, and how I've used it to build up a blockchain, or parts of it anyway. So, OpenSSL is extraordinarily popular. Now, part of the interesting thing here is that it came pre-installed on my Mac, and it came pre-installed on my Arch Linux operating system. But I have to admit, having worked on it for the better part of a week, the documentation here is not great. So, if we take a look at the docs, first thing we're going to find is that there is a difference in what we are talking about here. So OpenSSL often is conflated to talk about two separate things. So first of all, there is the command line tool OpenSSL, and that is going to allow you to pretty much do all of the same things that the library libcrypto can do, but it's sort of the command line version of libcrypto, if that makes sense. I think there's a clearer way to explain that. So libcrypto is the library of tools that we can use to do all the things that we're going to do today. And OpenSSL itself is a program that allows you to easily do those things. So let's stop being vague about this and go ahead and jump in and see how it actually works. What I want to start with is RSA key pairs. So RSA is a symmetric encryption algorithm. You'll end up with two keys, and one of them will be public, one of them will be private. And essentially the way it works is that you can basically use them interchangeably for locking and unlocking, but whichever one locks can only lock, and whichever one unlocks can only unlock. So if I have my private key, and you know my public key, you can encrypt a message, send it to me, and then I can decrypt it with my private key. But nobody else knowing the public key can decrypt that message. So it allows us to establish a method of encryption where it doesn't matter if this public thing gets known by a third party, so long as I keep mine private. So let's talk about how we are going to actually generate one of these key pairs. So here is my command line. We're going to do this in my desktop. Typically, I'll do this in a more secure location. And we are just going to use the command line program OpenSSL. And there are a few different, well, there are actually a lot of different things that OpenSSL can do. So this first one is just going to be generating the first part of the RSA key pair. Now, RSA is fairly complex, and I'm not honestly qualified to talk about the nitty-gritty nuts and bolts of how RSA works, but a short summary basically is that you're going to have these two really big numbers, and they are based on prime numbers, and you're using exponents with these prime numbers to generate them. Like I said, I don't understand that part of the algorithm. When we get to SHA, I can explain SHA a lot better. But we are going to first generate one of these really big numbers, and then to get the public key, we have to extract it from that first big number. So this part of this tutorial is going to be generating the first big number. So we are going to call it gen RSA. And now we can put in a few parameters. So where do we want to output this to? So I can say out will be, we'll just call it private.pem. And then I can say out form and specify PEM as well. Now, there are two different forms that we can output or input our keys in, and PEM is the default. It's sort of a human-readable key. It's not the most compact version of the key, but it is one that you can use. Big numbers excite me, yes. What is your name there? Organic Mint. I recognize that. Anyway, So a PEM is sort of a human readable version of this key. So we are going to specify our out form as PEM, but that's kind of unnecessary to do. And then I want to actually encrypt it. So this isn't necessary. I can, well, in fact, let's just do the base case. We could just, since we don't need to specify the out form, let's go with the simplest possible command. We're going to generate the RSA, whose output is private.pem. And now I want to specify the number of bits. Good morning, Joseph. Now I want to specify the number of bits that are in this private key. And the typical is 2048, I think it is. Yeah, 2048. And I'm going to double that because that's a more secure way to do it. The bigger your number is, the more secure this is going to be. So I use 4096, thinking I'm remembering those correctly. And if I remembered all of this correctly, we should just generate this private key. Now I can read the contents of this key. So I can say cat private.pem, and there is my key. You can see this is quite a interesting number, a lot of strange symbols for a number, but there it is. That's our private key. Now, this is a bit insecure, so anybody can just come by and read my private key, and part of the idea is that it needs to be private. So let's go ahead and encrypt this private key. We take our original command. Let's first remove the private key. Is that what I called it? Private.pem. And we'll go back to our original command. Now we put the number of bits last, so I'm going to insert this right about here. And what we want to do is specify an algorithm for encryption. And this is going to allow us to put a password on our private key. So I'm going to put in AES256. That is basically the SHA-256 algorithm. That's one I can't explain. But anyway, it's going to allow us to give a password. So if I do that, I can put in a password. I'm just going to say password. This is just an example. And now if I want to read the key, well, it'll still print out the key, but this is actually encrypted. So this is not my key. How can I demonstrate that? Well, trust me. This is encrypting it. So if someone comes by and reads this file, they actually can't. We can see the difference here with the deck info that it is encrypted. So I guess that's, you don't need to just trust me on that. But anyway, so someone can't come by now and just read this file. So we have a private key that is more secure, but now we need a public key that we can share with other people so that this can actually be useful. Remember that you need a public key and I need the private key so that one of us can encrypt and the other can decrypt. So let's get the private key out, or excuse me, let's get the public key out of the private key. We are going to do OpenSSL, and the command, the next part of the command changes. This is something I found a bit strange with the library. The next part of the command is just RSA, and I expect going into this, I expected that RSA would cover all of the steps. So it would be OpenSSL, RSA, then you generate the private key. OpenSSL, RSA, extract the public key. But instead they have different submodules for it. And I'm not really sure why. Perhaps there is a good reason for that, but I don't know it. Maybe if you do, you can leave it in the comments. Anyway, so we are going to use OpenSSL, RSA, and then we're going to in, and we are going to put it, what is that called again? Private.pem. And we can again do inform and specify PEM, but again, PEM is going to be the default. Now, as we go forward, we might actually want to change what file type we are using, but for now we're using PEM, so that's not necessary. And then we can just say out is going to be public.pem. Lost a connection on one of my devices. That is worrying me a little bit that we have lost a stream. I don't think we have. Sorry. Want to make sure that we're all still here. Oh boy. And there we go. Yeah, yeah, good. You all saw that. Excellent. Let's see if I can get that second display back up. Sorry about that. Very professional. Okay, that's back. And good. Okay. Quick. Great. Where's my terminal? Do that for now. Okay. We're back. Sorry about that. Happens. Anyway, so we're using OpenSSL, RSA. We specify that our input is going to be the private key and our output is going to be this file. But just specifying the file name public.pem doesn't actually tell us that this is going to be an extraction of the public key. In fact, it's going to assume that both of these are going to be private keys. So what we want to do is specify pub out. Now you could specify pub in or pub out, but here we want to extract the public from the private, so we'll use pub out. And I think that's all we need. It'll ask us for our password so we can decrypt our private key, and I just use password. And now it'll give us our public key. And now I can read the public key, and this is something that anybody can use to encrypt something and share it with me. But our actual interest in this in terms of the blockchain is slightly different. I want to show you something else we can do with these keys that is a little bit more relevant to what we're doing on the blockchain. But before we get there, I want to show you why I'm interested in the RSA public-private key to begin with. So on our blockchain, we need a way to identify users. And in your typical website, you're going to identify a user by having them log in. So you'll save their username and a password in a database on one server, and when they want to log in, they'll just specify those two parameters, and that one server will have a session for them, etc., etc. But on a blockchain, we don't really have that. One node isn't necessarily going to be online in a reliable way, and it's going to we need a way to make sure that whoever creates a block gets credit for creating the block. And this is how we are going to guarantee identities on the blockchain. So what we can do with RSA, typically the RSA algorithm is used in encryption to hide messages. So when you use HTTP, if I go to a website, we're using an RSA key pair to get that HTTPS so that the server can encrypt messages that it sends to us. And anyway, what we're going to do is slightly different. Rather than trying to hide what we are sending, we are going to kind of go the opposite way. We're going to use our private key to create a digital signature on the block. And then anybody can use our public key to verify the authenticity of that signature. So let's demonstrate this. I'm going to create a test document here. Ollie, you're making a show of yourself in public. I turn on Do Not Disturb, and yet here we are. Anyway, sorry about that. Okay, so I'm going to just create a document, and we'll just say, hello, Holly, in it. And what I can do is create a signature for that document. If I remember the correct code for this, OpenSSL RSA in is going to be private.pem, because we're going to use our PEM, our private key, to sign it. That way the public key is what we use to verify the signature. So like SFTP. I actually don't know much about the SFTP protocol, to be honest with you. Anyway, so we want to sign it with the private key. And what are we going to sign? We're going to sign test.txt DGST. And before that, and we need to specify where our signature is going to go. It's basically going to create a signature and store it in a file for us. So we can use that file as a signature. It's a bit strange, but you'll see it in action and it'll kind of make sense. So we want to specify where this signature is going to go. And I'm just going to say a file called signature. And the last thing I need is actually, before this, I need to specify an algorithm. And I want to use SHA-512. So let's review this thing because I went in the wrong order while I created it. We want to say OpenSSL RSA to specify which module of OpenSSL. Our input is going to be the private key, which is the key we are using to create the signature. And the signature is going to be placed into this file. And the signature is going to be created for this file. So what this is going to allow, if it actually works, it didn't. I made a little mistake. I specified the wrong algorithm. I was supposed to do AES. Or am I forgetting blowfish? I want to know what that is. Let me quickly, very professionally, search for what the signature key is, just so we don't waste time. What am I forgetting? DGST. That's it. My mistake. Okay. So you see, this is again where OpenSSL is not behaving in a way that I would expect. So there's a second submodule for creating these digests. And I guess that makes more sense than separating the generation of a private key from the extraction of the public key. But still, it just surprises me that it behaves that way. And yeah, anyway, quick Google search and we're on the right track. So DGST, and now I need to specify a digest algorithm. And here's where I can do SHA-512. And SHA-512 is a hashing function. So it's in the same family of things as this RSA encryption, but a hash is slightly different in that it is a one-way thing. So when you hash a document, there's no way of going back to the original document from the hash. It's just supposed to sort of be a fingerprint for the data. Whereas the encryption algorithm, the RSA, is supposed to be something to encode and decode. There's a slight difference. What we're going to do is create a SHA-512 digest of the data with the private key, and somehow that can be extracted with the public key to guarantee the authenticity. Now, I have to be honest, I don't know exactly how that works. No, I don't know exactly how that works. So there's some magic going on here. That's unfortunate, and that's sort of the downside of using a third-party library. But the upside is I don't have to learn it right now. Anyway, so let's press on. So I'm going to create a digest of SHA-512, and let's make sure I'm still remembering this correctly. We are going to not verify. We want to sign using our private key and output there this file. Okay, so sign private.pem -out is going to be signature, and then we want to sign test.txt. We need our password for the private key, as always. And now on the desktop, we have this signature file. And this is, I always like them to be aligned. Anyway, this is something that we could send. So let's imagine that I want to send you this file, but let's pretend this is a very important file, and we really need to guarantee that what you receive is exactly what I sent. We can create a digest of this file, so a hash of the file. Now what we are also doing is combining that with the public key. So again, I'm not quite sure. Maybe here's a guess at how it's happening. I don't know why I'm going to just take a wild guess on a live stream, but here's something that makes sense to me. If you hash this file, so if I just run a SHA-SUM -a 512 algorithm 512 of test.txt, that is a SHA-512 hash of the file. So maybe what's going on here is you use the private key to encrypt this hash. Then you use the public key to decrypt the hash and compare it to the actual hash of the file, and that's how you can tell that it's the same. Maybe, but the point of this is twofold. The hashing of the file guarantees that the file is the same. It guarantees that the file has not changed. And the encryption using the private and public key guarantees that whoever created that file, or whoever created the signature at least, was in possession of this private key. So if I was to send this to you and we wanted to guarantee that both this file was exactly as I made it and that I was the person who made it, I would send you these 3 files. And what you could then do is run the OpenSSL DGST -verify, and we need the public key here, so public.pem. And what's next? I think we also need to specify SHA-512 again. This part's a little fuzzy. I didn't do this a lot because ultimately I'm not interested in doing this from the command line. I'm interested in doing this in C. And so I'm just kind of demonstrating the features here. So verify public PEM. Let's check our Google search just to make sure. Verify public PEM signature. There we go. Yeah. So I can just run this. Doesn't like that. Did I miss something? DGST algorithm verify public signature my text. I forgot to specify that at the end. Nope, I ruined it. Oh well. Got to put the file. I need to. The signature is for a particular file, so of course we would need that anyway. And then it tells me that verified OK. So this has guaranteed both that my test.txt file is not tampered with, it is exactly as I intended it to be, and that the person who created this signature was in possession of this private key. So we have guaranteed the authenticity of the file and the authorship of the file. So how does this play into the blockchain? So first of all, remember that OpenSSL is a command line tool, as you've seen me using it here, but it is powered by a library called libcrypto. So if we go back here to our documentation and let's see, manual pages, master, libraries. So yeah, here's the crypto library. Here's all the different functions. And this is why I am making this video largely, because this is very unpleasant to navigate, I have to say. While the library is good and robust and kind of ubiquitous, this documentation, man, it's rough. So we could just pick anything in here. And what I would say the real issue here is that it is highly self-referential without a clean way of navigating those references. So this is talking about CMS data create EX. Now, I'm going to find something different here. That's something that I've actually been using and that we're going to see in the blockchain. Okay, this EVP P key. Okay, most of the things that I was doing in this blockchain are focused around these EVP structures. And having been working on this for a fair amount of time now, I still don't know what EVP stands for. It's just not anywhere in these documents. So if we go to, let's see if I can find an actual EVP function. There we go. There's a bunch of them. Let's do this one. Okay, so here's a list of the functions with what their input is and their output. And here are some descriptions of some of them, but you'll notice that what an EVP is never defined, or there's no way for me to find out. It does tell me that the EVP cipher routines are a high-level interface to certain symmetric ciphers, but beyond that, we don't really know. So this library is a bit of a black box, but it works really well. So we're just going to have to navigate this black box as best as possible, and I'm going to show you how I have found certain things. So let's take a look at some code. Anyway, here is what an account is going to be on the blockchain. So since we can use a public-private key pair to identify people or identify authorship, then what we can do is essentially say that one key pair is an account, and we can load those accounts in as our users. And this even comes with the handy feature of being password compatible. So you can even password protect your account. And this translates really well to a distributed system like a blockchain because it's dependent on a physical file. So I can take my public-private key pair. Well, my public key is kind of dispersed far and wide, so that I should be able to find. But my private key, I can simply take that file, move it to another computer, and now I can log in on that computer. So we don't have to have a central database of users, and everyone is kind of responsible for the security of their own account. And it's going to be dependent on this physical file, which can go and be anywhere. So we need to be able to do a few things. First is going to be creating an account. So it's done through this EVP P key structure, and there's sort of two things that happen here. First, we have this EVP P key, and this is the variable or the data type that is going to actually store the key itself. And then we have this P key context or CTX. And again, since this is a bit of a black box, I don't quite know how that works. Joseph, the top of evp.h is if and def header envelope h, so EVP might mean envelope. Oh, that makes sense. Yeah, that makes sense. That's a good, thank you. Until we hear otherwise, it's an envelope. Okay, so this envelope P key context. Anyway, so we have to have a context in which to build things and the thing itself that we are going to build. It's a little bit strange, but anyway, first we create those two variables, and then we are going to go into a process of performing these particular manipulations. Joseph, there's an explanation in doc/ss.txt, which might be worth looking into. Thank you. I don't read documentation usually, so it's not surprising I missed it. I do prefer actually to blindly go into projects and just kind of work my way through it. But if someone can point out exactly what I need to read, then I appreciate it. Anyway, so the first step here, when we go into these EVP keys, you're going to notice that libcrypto, which, by the way, I'm including like this. I did not need to install it. It came pre-installed on Mac OS, comes pre-installed on a lot of Linux distributions, so you should be able to just use these include statements. Just make sure you link to the library. So if you're using GCC, for example, you're going to want to link to the static.a file, and what you're going to do is all of your .c files that you want to compile, and then at the end, just -l crypto. And that will link it to the library so that everything will compile correctly. Anyway, you're going to notice that there is a pattern in how we work with these keys. So we start off by creating these two variables, a key or a P key object to hold our thing, and a context in which to manipulate that thing. Okay? In this case, it's the process is a little bit shortened, but it's similar. We're going to initialize the context, then we are going to perform the operation, and then we are going to arrive at a final state. And that actually will be rather explicit in the future when we see more of what this can do. There's an awkward shadow going across my... very menacing. Anyway, so what I am doing here is basically saying that, well, we have our initial context, and what I want is an RSA key pair, or a key gen, a private key, with 4096 bits, 4096 bits. As I did before, it's a little bit more secure to use higher bits. So I set those bits, and then I generate the key. Okay, so now I have in this variable key, I have an actual RSA private key, but I need to actually write it somewhere. I need to store it. So I'm going to write it to a file. First, I am going to create a file. I've done some work with variables here to make it a little bit easier. So for example, if I go to account.h, we can see that I defined where the profiles are going to go. This is going to change actually in the future. Not everybody is named Eric, believe it or not. So we're going to have to make that more appropriate for the Linux operating system, is probably going to be our primary target. But anyway, we're going to open up a path to this file, and we have passed in like the name of the account. So this would end up being /users Eric desktop eric.der. Okay, so first I'm just checking to see if that already exists so that I don't overwrite any keys that are already there. If there is one there, it just aborts the whole process. Okay, now what we do is open the actual key file to write to it and use this function here, I2D private key FP. Now, first of all, I'm using a different format here. So what we saw when I was generating these files is a PEM. And remember, this is a human readable format. So cat, we can see that it starts off with these actual words that we can read and things like that. But there's another way that we can actually generate the key that is a little bit more concise. So if we sacrifice human readability, let's, for example, just get info on that. We can see that this is 3,326 bytes. So let's generate a private key of the same number of bits. Let's put it in a different format. So OpenSSL gen RSA. We're going to start it from scratch rather than using the old one as somehow related. Gen RSA dash out is going to be .der. So DER is an alternative raw binary format that's much more concise. We'll have our private.der, and our out form going to be DER, and is that it? I'm not going to put a password on this just for simplicity. I think that's it. Of course. Forgot the number of bits. 4096. No? Didn't like that? Let's see. What was my original? There we go. So what was I getting wrong? Let's actually learn from our mistakes. Gen RSA-out private.der out form. I suppose it wanted me to specify an algorithm to encrypt it, but you don't have to encrypt it. Let's see if I don't. Yeah, it really wants me to encrypt it. No? Something's going on. Maybe it's key form instead of out form. Let's Google it. Sorry. Again, I'm more interested in using libcrypto, so these particular commands I don't remember. Let's see. Well, here's what we can do. Okay, let's change what I was saying, and instead of generating a totally new one, we're just going to extract a DER from this private. So it'll be exactly the same key, same private key, just in a different format. Let's do that instead. So OpenSSL RSA-in is going to be private.pem, and -out is going to be private.der. Say out form DER. And what we usually would do here, or what we did the last time, was specify pub out. But we're not actually going to do that because both of these are going to be private keys. This is going to be an exact copy of our original private key, but it's just going to be in a different format. It's going to be in raw binary rather than that human readable form. So we need to put in our password. That's not the password, that's my actual password. Okay, so now we have private.der. So this is exactly the same key, just in a different format. And if we look at this, we can see that it is significantly smaller, about 1,000 bytes smaller. And while that doesn't really matter for the private key in our case, because that's just something the user is going to keep on their local machine, for the public key, it actually makes quite a significant difference because we're going to need to be sending this to other people. So we're going to want to use the DER format. And that's what this I2D function does. It takes as an input the key that you want and writes to this file the raw binary of that key. So this is going to save our private key to a file. So I2D private key FP. And there's a lot of I2D functions. So if we do I2D private, we can see we have private key FP, private key bio, private key FP with PKCS8, all kinds of crazy stuff. And so there's a lot of different things here. And another issue that I was running into a lot is that a lot of this is deprecated. So there are things that'll do exactly the same thing. So like this right here, I2D DSA private key FP is going to do the same thing. It's just deprecated. So often online, you'll find an example. Like if I want to find an example of how to load a raw binary. So here we're saving our key to raw binary. Now, what if we want to load our raw binary back to a key? Well, the examples you might find online will be deprecated, and there's no indication sometimes what the alternative is. So there's some navigation to do here. Now, I have put in some work to make sure that nothing in this library or nothing in my code is deprecated. So my Mac is comfortable with everything that I'm using here, and actually I think that my Mac is being particularly picky, marking certain things as deprecated that are not. So all of the files, or excuse me, all of the functions that I use, you should be safe to use. And by the way, all of this code that I am using is available on GitHub. There's a link in the description, and this is the blockchain project. So we are in the accounts here. Anyway, let's hop back in. So I2D private key FP. We are taking this key that we have just generated up here, and we're saving it to a file on the disk. So this is creating a more permanent version of it. Okay, we close the file, and now I need to get the public key out of it. And actually, this is a fairly simple process. We already generated the key up here, and all we need to do is just use basically the same function, but for a public key instead. Now, there's one downside here. Now, I have not found how to put a password on these I2D raw binary files. So if anybody out there knows how to get a password on these files, please let me know, because using this I2D method, I can't seem to find a way. And I think we would be better off allowing people to put passwords on their files. That being said, there is no reason on our blockchain why we can't use PEM as the format for the private key. Remember that we're using this raw binary format for the public key because we're going to be sending it, and we want to be efficient with the data that we're sending. Why that is will make sense once we start looking at these files. Anyway. Okay, so this just creates an account. So let's see. I'm going to go over to my test file here. I created some little unit tests. And let's see, all we want to test is the create. So let's actually comment out all of these. We're only going to be running one test. And then our actual test file, we're going to run one test. And it is going to be this one. Okay, so if we run this, completed with 100% success, hooray, and here we go. I should have deleted these files first. Let me go ahead and do that. We can actually see the change. Let's run it again. Okay, 100% success. And here are our two files. And if we look at the size of them, here is the public key. The public key is going to be quite efficient, 550 bytes, and it is consistent in that, which is very important for us. So this is a very small file, and it's also a very consistent file. So we are going to be able to send it with ease. I'll show you how we are sending it in a bit. Anyway, the private key then is right here, 2348 bytes. So we have our account. Now, we've created this account, but we also want to be able to activate an account. And what this is going to involve is actually loading our files. So we're going to do the exact opposite of what we just did. Instead of I2D, we want to do D2I public key or D2I private key. And where we are going to store this actually is in, I created this account structure, and it just has two EVP keys in it, and I just made it so that it was easy to pass these two variables in as one and just make it consistent throughout. I basically pass this variable through to all the functions so that it can be used easily. And this is our logged in user, so to speak, a session, if you will. Whoever is currently using the program should activate their account, store their public and private key in here, and then we can use it to do stuff on the blockchain. Okay? So our activate is going to be a process of loading our raw binary file in and storing it in this key here. So we've passed in this account by reference, and we're going to basically put the contents of our key file into this. That makes sense. And there's a bit of a nuance here. So there's no reason why I couldn't just load my key file and read in 550 bytes of data from it, and there I have my raw key. But that's not in a usable format yet. So we need to actually extract it and turn it into one of our EVPP keys. That way we can do things with it. So if we just want to send it from me to you, then we don't need to worry about this. I can just read in those raw 550 bytes, send it off to you, and we're good to go. But if I want to actually encrypt something with it, then I need to turn it into one of these envelopes, as Joseph told me they're called. Okay, so this loads it in and turns it into one of our keys for us, and then let's see, we do the same thing with the other, and something that was a bit interesting. I don't remember exactly what the, let's see, what were the arguments here? Okay. So this is doing the same thing, loading something in, but using the private key. And it gives us a few additional options. So we pass in the file that we are trying to read. We give it a p key reference that will end up storing the key. And then we have this libctx, and I don't know what prop q is, but these are additional things. And maybe this is where we can do some stuff with a password, but I don't actually know what these are, and here is another example of the documentation being self-referential in a way that's not really helpful. It will tell us, for example, if we look at the documentation for this, it's really easy to find, fortunately, but I'm just going to type this into Google. First link that comes up. And what I'm looking for is this, OSSL libctx. Let's imagine we don't know what that is. Indeed, I don't. So, where is it referenced? There we go. In this case, the supplied library context libctx and property query string propq are used. So it just sort of assumes that you know what that is, and it's I mean, just a Wikipedia style thing would be really useful here, where I could just click on this and see what that actually is, but no such thing exists, and so it's a bit difficult to navigate. So I'm just putting null in here for now. If you know what those two things are and tell me, I would really appreciate it. So let's keep on rolling. This is how we activate an account, and we can do that through our tests as well. So let's see. Just so you know, with my unit tests here, I often run into trouble if I try to create the account after it already exists. We're going to not do that anymore. And how many are we doing? We are doing 4. Okay, this is going to unsuccessfully create. So as you saw over here in create, I will not create a file if the user already exists. We don't destroy pre-existing files. So it's testing to make sure that's true. And then we want to successfully activate. So this is going to load our two files, our public and private key, into our account and test to make sure that that has actually worked. So that is our successfully test activate. And here's another version where it fails. We want to make sure it actually does fail. And deactivate is quite simple. We just turn all of those to null. So if we come back to test.c and undo that, no, we don't need to do that. We're just going to run it. I will let it access my desktop. So, okay, so we are getting 100% success. And what it is testing for is that in the successful create, we didn't run that one. So here it tries to create an account with the name that already exists on the system. We can see on my desktop I have these two, test.der, test.public. It would try to create exactly the same file names, and since it already exists, it just fails. So a failure in this case is a success, so we have succeeded there. Then we want to activate them. What's being tested here? So at the end of activate, we are testing to make sure that these two fields have values, and indeed they do. They start off as null, and they get a public and private key. So now we can pass our user account into new functions and just access these two keys. Okay, and what else did we test? Unsuccessful. We try and activate a user that's not there. That works obviously, and deactivate just confirms that these two fields have been turned to null. Easy. Okay, so that is kind of how our account works. Your private key and your public key, this key pair, is your account on the blockchain. So why would we do it that way? Why would we need a public key? Well, we are going to be signing things, and we are going to be signing our blocks. Now, before we get into this, I need to get some water, so I'm going to take a 5-minute break, and I will be right back. And I'm going to be smart and plug in my Mac so that the battery can start charging, because we're getting low here. I'll be back. Okay. Turned. Battery is looking okay for now, so I'm going to put the camera back on. Probably won't last long, but that is okay. All right, so one of the problems with doing this I want to talk about is trying to explain some of these rather odd algorithms while also giving you the big picture. So I want to be thorough and explain what RSA and a hash is, while also showing you how they're working together on the blockchain. So here's my recommendation. If you are familiar with RSA and hashing algorithms in general, then watch this for the big picture of how they're being implemented into the blockchain. If you're not familiar with them, then watch this for what they are and why they are used. Okay, so RSA is used for encryption, whereas hashes are used for fingerprinting. And with the stuff we're about to get into, this is going to be more of them kind of playing together and working together in a somewhat complicated way in order to achieve the blockchain and give us all of the properties of a blockchain that make it what it is. What you're going to find is it's a little bit difficult to conceptualize how this all works. And a lot of it is because it's not like you're coding in these properties. It's sort of like they are emergent properties from the properties that you give it. Okay, let's take a look. So our block is going to consist well, it's basically going to have two main things. It's going to have headers and it's going to have data. Any data, you can put absolutely anything in this field. Now, when you first instantiate one of these structs, it's only going to put 1 byte there, but actually you're going to do this, if I show you the context of creating a block, we're going to use malloc. We're going to put it on the heap, and this allows us to make it any size we want, and we will just reference, where'd it go, block.h. We're just going to reference data as an address. So this just gives us the address of the first byte of available data in whatever size block we have constructed. And the headers are what identify this block and make it part of the blockchain. There are two types of headers that we can have. I call them incidentals and credentials. The incidentals are just things about this block that we might want to know, such as the size. the time that it was created, the previous hash, the thing that links it to the other blocks that are already in the chain. Those are all just incidental to the block itself, but the credentials validate it and make it part of the chain. So there are 3 fields here. First is going to be the key. This is going to be your public key, that raw binary. Note that it is 550 bytes. By the way, this byte data type is just an unsigned character. Okay, so it's just 1 byte. I just changed the name of it for semantic purposes. Okay, so we have 550 bytes for our key, so we write our key in there. And then we have 512 bytes for our sign. Now, I don't think I emptied this. Here we go. If we pull back my signature from before, this is a, I think, raw binary, 512 bytes. So we can now put our signature into this field. And then our nonce is something that we use for the hash generation or the difficulty. Okay, if you saw my video where I do this in Python, then you'll know kind of where that is going. So what we can do, we can create a block, and when I want to add a block to the blockchain, it's going to go through this process where I first create it by, well, here I'm loading in my public key. I need that separately. Do I actually need to do that? Okay, sorry, let me delete that. So that was a test that I was running earlier, so it's actually just writing my, I'll show it to you. This is writing my public key to my desktop in a file called test, and I was just doing that to make sure that the integrity of the account was preserved when it got passed into this function. So that was an earlier test that I was running. We don't need that. What I'm going to do first when I'm actually creating a block through this process called mining. I'm going to mine my own block here. Now this is a good opportunity for me to get sidetracked again and talk about how my blockchain might differ from other blockchains. Okay, I am not building this in reference to any other blockchain out there. This is my own design for a blockchain. So I am not teaching this as this is how other blockchains work. Does Bitcoin use RSA key pairs as accounts? It might. I think it does, actually. I have a feeling it does, but I don't know. And what about Ethereum? Do they create blocks this way? Probably not. Okay, this is my version. So while a lot of the principles you will see in action here are kind of universal to blockchains, there are some particulars here that are for my blockchain. So let's go forward knowing that. So we are going to allocate space for the block. Now we have passed in the data that we want to put on the blockchain and the size of the data. Remember that this can be whatever size we want. We can make this thing petabytes if we want to. It doesn't matter. So we are going to allocate however much space we want for this block. And then we are going to set a few of the credentials. So the nonce needs to start off at 0, and then we're going to put a timestamp on the block. We'll go into some particulars about that a little bit later. I want to talk more about the OpenSSL parts here. And then we are going to put in a few more of the incidentals. This is all just details. Not that it's not important, but we don't need it right now. It's not what we're focusing on. Where it gets important is when we come down here to this next function of signing the block. What we are going to do is actually the same way I created a signature here for that test.txt, we're going to create a signature for this entire block that I have just created. Or not actually the entire block, just the data in the block. So I pull up my block.h. We're going to sign this field. We're going to create a signature for it. Okay, and the way we do that is here. First, I used memset to set all 550 bytes of the key to nothing, just so it was empty. And then I used this I2D pub key function. Now, remember that we used I2D pub key FP to write it to a file. Taking off the FP from the end with this similar function allows us to write our public key EVP object to raw binary or raw bytes, wherever we want. So basically what I'm doing here is taking the public key that I saved in my account struct, and I am writing it to this field on the block. So I'm putting the public key into the block, okay? And I say the size of the block. Okay, so when I put the field of size in up here, where is it? Here we go. Block size equals the size, so the size of my data plus the size of my block headers. Okay, so when I'm talking about the size of the block, I'm talking about the entire structure. But down here, I want to talk about the size of the actual data. So what I do is extract the size field from the block, and I just subtract the size of the headers. Okay, so since the headers are predictable, there are no pointers in them. Let's see. You can see that all of these are concrete types and sizes. There's the battery. I gotta lose the face cam for some time. Goodbye. There we go. Okay. Since all of these are concrete, I give exactly 550, 512, and I specify that this structure is packed. I can predict the exact size and shape of my headers. So that allows me to very easily just subtract the size of those off of the block size and know the size of the actual data contained within the block. Okay, so here we are going to have our EVP thing again. So we need our EVP context. So I create this EVP context pointer, and I set it equal to EVP MD CTX create. That's typical. I'm actually going to change this so it looks a little bit more like it does later. And that I'm not too fond of either. No. Okay, so the EVP MD CTX create, if I'm not mistaken, is just a macro redefinition of this. But throughout the OpenSSL, or I should say libcrypto library, there are functions that basically have the same naming conventions as this. So that's why I decided to make the change, just so that I'm following the same naming conventions throughout my program. It's going to do the same thing. We created a context, okay? And now we're going to use a function called EVP digest. Okay, so this is a family of EVP functions. There's EVP digest sign, EVP digest verify, EVP digest that, just EVP digest. And we're going to go through our process here, okay? We are going to initialize, we are going to put our data into it. This is called updating, and then we are going to arrive at a final state, okay? So we initialize it by putting it in the context, telling it that we are going to use the SHA-512 algorithm to create our signature, the same way we did here. If we go back to this one, when we signed it, we used the SHA-512 algorithm. We're going to do the same thing here. And OpenSSL provides this little function, EVP SHA-512. It returns an EVP structure that represents the SHA-512 hash algorithm, whatever that may mean. Okay, I don't remember what these fields are, but we pass in null. I think there's something in there about a digest callback. I don't remember. Anyway, I pass in null there. We can look up the documentation later. And then I give it my private key. So this initializes the process of signing. So we are creating a signature here using these three parameters. Okay, now we're going to update the signature. Updating is where we pass in the actual data that we are interested in. So we give it the address of our first byte of data, which is just the address of that field. And then we give it the size, which again is the size of the entire block minus headers. Okay? And then we arrive at our final state. And this I don't actually know what this does, to be perfectly honest. I don't know what final is in this, but basically we arrive there. I guess maybe it needs to do some cleanup at the end. We arrive at our final, giving it the context, and this variable here, I think it is putting the length in that. And what is the difference here? So I think I'm repeating this for error checking purposes. Am I? Or am I just unnecessarily doing it twice? I think I am unnecessarily doing it twice. Yeah, let's get rid of that. So that shouldn't be null. What this final is going to do, I'm worried that that's not the same. Is that exactly the same? It is. Okay. Okay, so what this is going to do is put our EVP structure into its final state, whatever that is. So we're going to get our digest out of that. That's how we're going to extract the SHA-512 fingerprint. Okay, so we give it our context, and here it is where it's going to put the digest. Okay, and length is how long it's going to be. So we know that we are using the SHA-512 algorithm, so this length is going to end up being 512, so I suppose it's unnecessary, but essentially what's important here is we are going to be writing the signature that this creates into this field. So over here, our lock is going to become the SHA-512 digest. So in our block, we are going to provide a key and a lock. And this is going to allow anybody to validate who created this block. So since I made it, I want credit for having created it and added whatever data this is to the blockchain. So I'll use my public key to identify my account, and I will sign the data to essentially guarantee that I was in possession of my private key. And this is how I will have a secure account that allows me and only me to say that I made this on the blockchain. Okay, so that's sort of your ownership on the blockchain. Okay, so the process of validating the signature is going to be very similar. The same way we just had to do up here, or sorry, over in the account file. The same way we just flipped, instead of I2D, we did D2I to write raw binary to a file, or whatever I was doing over there. We're going to do kind of the same thing. We're just reversing the process when we want to validate the signature. So again, we're going to start off with a context, and let's do... I'm nervous that that's actually going to break it, so maybe I shouldn't be doing that. If it does, I'll fix it, but that's okay. Anyway, and we have our EVP P key null, and I should make that P key new. Okay, so what's interesting here is something you need to be on the lookout for when using libcrypto is that you're often going to create these EVP structures and others using a function called new for whatever structure you're creating. And this is actually going to allocate space on the heap. So at the end of your function, make sure that you free it. OpenSSL provides special functions for freeing their things. So just make sure you go back and check, make sure you're freeing things. I wasn't doing this earlier, and it would very, very quickly start burning through memory. So, okay, it's going to be basically the same process. I'm going to create a context, and then I'm going to create a key, but now I'm going to use D2I. So if we look up here, I use I2D to write my public key to the block header key. Down here, I'm going to extract the key from that field. So it's basically just the reverse process. I here take an EVP key and write its raw binary to the field. Here I'm taking the raw binary written in the field and turning it back into an EVP key. This makes it very concise for sending, a mere 550 bytes, and also makes it so that I can easily load it back in and actually do things. because now I need to do the same process using an EVP digest, but now we are going to verify instead of sign. So we're going to initialize it by passing it the context, our SHA-512 reference, and the key that we just extracted. We're then going to update it with the block's data and that size that we explained earlier, and then we are going to arrive at our final state. Is this going to... Okay, yes. So this is, rather than writing our final into this, it is actually going to compare the final that it gets to this. So this is sort of our comparison field. What did we get, and what are we actually measuring ourselves? And if these are the same, it will return true. I've freed the keys, and we have verified our signature. So if a block is to be accepted on the chain, it needs to provide a lock and a key that works for the data. This is going to guarantee authorship and some amount of authenticity. Okay? So if that wasn't enough, let's talk about how we are going to mine the block a little bit further. So after we sign the block, now we need to enter the mining zone. So here's where difficulty comes in. And I'm sorry, I'm getting a bit of a sore throat here, so I'm going to grab my water right back. The sweet refreshment. Okay. So now we're going to talk a little bit more about hashes. So far we've been talking about RSA encryption. Now we're going to sort of pivot to the SHA-512 algorithm a little bit more. Now remember, a hash is a fingerprint of a file. Okay, and part of the appeal here, let's see, do I still have my test file? No. So I'm going to create it. Touch. Still say hello to Holly. Okay, so now I can use, actually I could probably use OpenSSL to do this. I almost certainly could, but I don't know the command, so I'm going to use a different program called SHASUM A512 of what? test.txt. This is going to give me my SHA-512 hash for the function, or the digest of it. Now this is a 512-bit number, or we could think of it as a 64-bit hexadecimal number. So this represents a really, really, really big number. Okay, and one of the keys to the SHA-512 algorithm is that if I change a single bit in test.txt, it has a 50% chance of changing every single output bit. Okay, so if I go and I am just going to add a space on the end. And when I run the same program to get the SHA-SUM, it's going to be completely different. Okay, so changing anything about the file is going to change the output completely. Okay, so it's not random. In fact, every time I run this, it's going to give me exactly the same output. So it's highly determined, highly based on what is actually in this file, but there's no way to predict what it's going to be. And it represents a number between 0 and 2 to the 512th power. That's the 512. Okay, so what we're going to do in order to mine a block is establish a difficulty. So where is it? Validate hash. Okay. Here I'm using the big number section of the libcrypto library. Okay, so C, our data types have a finite size. So an integer has 4 bytes. So the largest possible number you can store in an integer is however big that is. And you could use bigger numbers like an unsigned long, and that's going to give you a much bigger possible number. But what happens when we need something even bigger than that, something like this? This number is way too big to fit in any data type in C. So what we need is something called arbitrary precision, the ability to make a number as big and precise as we want. Fortunately, libcrypto offers this. It's actually, I've tried doing it myself in the past. It's more complicated than it seems. But anyway, they've done it for us. So what we're going to do is create these big numbers, and they are going to be representing the actual numeric value of a hash. And what we're going to do is hash our block. So, well, first we're going to establish a difficulty. So remember that the algorithm, the SHA-512 algorithm, is outputting a number that is between 0 and 2 to the 512. So what we're going to do is essentially put a restriction on what we're going to accept. So 2 to the 512 power minus whatever difficulty we want. And remember, that is, the power is 512 minus x. And I've been playing around with some different algorithms here. Actually, Joseph and I were discussing earlier some different versions. I don't remember exactly the word he used to describe the one he recommended, but this is the algorithm that I have come up with. Okay, the log of the square root of x squared plus 1. It's a little bit odd, but there are some properties to it that make it kind of ideal for what we're doing. So first of all, it has the point 1, 1 on it. Our x value is 1. Our output is 1. By the way, x. What is x here? X is going to be the size of your block. So we look when we're doing the calculation. I put in the same function here, kind of written in C speak, log square root of x squared plus 1. That is going to be log square root of x squared plus 1. So our x is going to be the size of our block, and it's the total size. We're not subtracting the headers here. Okay, so the smallest conceivable block is 1 byte. It's actually impossible because of the headers. It would never be 1 byte. You're going to need at least 1,000 bytes. So you'll never have an input of 1. But if you were, the output would be 1. So that's kind of a nice base unit for our difficulty. And then if we have a megabyte, which is 1,000,000 bytes, our output is 10, so a difficulty of 10, which seems fairly reasonable. And then I don't know what that is, 1 billion is going to be a gigabyte, is 21.25. This is the largest number that we can store in a C data type, so this is the largest practical file that we can store, and this thing is several petabytes, so no problems there. I think it's 16,024 petabytes, or pebibytes to be specific. And that gives us a difficulty of 93. And then this absurd number is the theoretical maximum. So once we have an output of 512, we will accept 512 minus 512 hashes, which is just 0. So we are not going to accept anything. So we cannot store on the blockchain a file bigger than this, but this is like billions of pebibytes. It's way bigger than anyone would. We're talking atoms in the universe sort of sizes here. No one's going to be creating files this big, and if they are, I want their computer. So this is the theoretical maximum, and that's where we get our 512. Why I've chosen this algorithm for now, or excuse me, this model for now, is that this area of exponential growth, where the changes are the most significant, it sort of scales really well. As our file size increases, essentially the significance of a single byte decreases. So up here, we're looking at 10 to the 7th. That's like maybe 10 megabyte file, our difficulty is going to be 13. And as you can see, as I go up, the difficulty is changing fairly rapidly. It's increasing rapidly. But as my file size increases, that speed slows down. So it makes it more reasonable. If I am going to mine a gigabyte, then it's going to take longer, but a gigabyte plus 1 byte is not going to take significantly longer than just 1 gigabyte. Whereas mining 1 byte versus 2 bytes, that's a significant difference. So that's kind of why I've chosen this. The values between a megabyte and a gigabyte, kind of where most files are reasonable, and it has this nice property of the value of a byte decreasing with size. So this is sort of the formula that I'm leaning towards, but I'm open to suggestions for this. Okay, so we've set our difficulty according to that formula. And then what we're going to do is establish a target hash using these big numbers. And this is basically going to be the biggest hash that we will accept. And then what we're going to do is actually hash the block. I'll show you that in just a second. And we will create our hash and convert the resulting digest into a big number. So now we have our target as a big number, and we have the hash of this block as a big number. So all we have to do is compare them. And if it has worked, if the hash of the block is less than our target, then the proof of work has succeeded and we can accept this block. Okay, so up here, where's mine block? In this while loop, if it has succeeded, we will stop this loop and we'll move on. But if it hasn't succeeded, we're just going to increment the nonce by 1 and do the process again. And this is the work that your machine has to do in order to mine a block. Okay, let's look at the actual process of hashing a block. Same as actually before, very similar to the thing with the RSA. We're going to create a context. We are going to initialize that context with a context variable, the algorithm we want to use, and we should be putting a key here, should we not? I guess since we are not using keys, we're just using SHA-512, we don't need anything there. So we initialize our EVP digest thing, and then we update it, passing in the actual data and the size of that data. And then we arrive at a final state, storing our digest here in digest, which is actually going to be passed in here. So that's how we are getting it out. Where? Here. We pass in digest, we get it here, and then we can convert it into a big number here. That allows us to do the comparison here, and et cetera, et cetera. And notice I am also freeing all of these things when I'm done so that we can keep our memory leaks to a minimum, meaning none. Okay. So that's how we hash a block. And that's how we mine a block. So as our blocks get bigger and bigger, the more data you're trying to input into the system, the harder it's going to be to hash and the longer that's going to take. But the value of doing so, if you think about in Bitcoin, the value of mining a block is sort of just dictated. I think it's 12.25 right now, maybe 12.5 Bitcoins if you mine the block. I don't know exactly what it is. I don't really keep up with them. But anyway, on our blockchain, the value of mining a block is going to be equivalent to this. Joseph, or is it defined before the hash? Just curious. Is what defined? Oh, do you call the difficulty integer again? You mean this one? So, yeah. So, okay, I'm glad you pointed that out. There's a few things to say about this. So first of all, if we look at the graph again, you'll notice that here, for instance, that is a irrational number, okay? And that is going to cause a problem on our blockchain because of exactly what I was just saying. The value of mining a block on our blockchain is going to be equal to the difficulty of mining that block. So if you mine 1 megabyte, your reward is 10 units of whatever cryptocurrency we are using. We'll call it credits. So if you are mining a megabyte file, your reward for having added that to our blockchain is going to be 10 credits. If you mine 1 byte, the difficulty is 1 and your reward is 1 credit. So here we have an irrational number. And that causes a problem because we don't want to have to calculate with irrational precision how much value someone has contributed to the blockchain. So what we're going to do, I didn't mean to do that. What we're going to do is take whatever value we get here and store it in an integer, basically just truncating it. We're just going to cut off any decimals. So we're only going to use integral values. Okay? Now, I get this as an integer here because I need to do this calculation using these functions in C, which work with the native data types. But then I need to actually turn it into a big number. So to answer your question, Joseph, what I do here is I create a character array of 8 bytes, and then I use sprintf to basically take this difficulty and put it into this string. And then I use big number decimal to binary, where it's going to basically do that conversion for me. So I'm going to basically put difficulty into exponent by doing this conversion. So I reference it again right there. Difficulty relates to the size of the file being hashed to the reward to the miner. It's the same thing. So if I like, let's say I'm sending a structure that is a total of 1 megabyte. So the difficulty of that is going to be right here, 512 minus 10. So my hash, the hash that needs to result from this algorithm, is going to have to be less than 2 to the 500 second. Okay, so it's essentially all of the values between 2 to the 502nd and 2 to the 512th I am no longer accepting. So I'm just going to have to keep generating them, changing 1 bit of data until I get a hash that suits that, if that makes sense. So the size of your block, the total size of your block, determines how difficult it is and is also equivalent to the value of that block. So for my megabyte file, I'm going to have a hash less than 2 to the 502nd, and I'm going to get 10 credits as a result. Gotcha. Cool. Okay. So where were we? We've got our thing for hashing the block. Let's see. Our mine, we validate the hash. So we enter this infinite loop, just incrementing this nonce, changing 1 bit of the data until we get a hash that works. We confirm that the hash worked. And okay, now the last part is to extract that hash and put it. Now we need to put our block into a permanent file. So we've created it. We have incremented our nonce such that the hash of it is valid. And now we need to save it into a file. So I am going to hash the block 1 more time so that I can save its digest here. Now I'm going to create a big number and again convert my digest into a big number. Then what I can do essentially is I have a global variable set for where the blocks go. It's just my desktop at the moment. I'm going to add that hex value of this big number to the path with .block. We'll open a file for that path, and we will write all of that data to the file. And then that file becomes our block. So let's see. Test file. We're going to cut out the unit tests for the account, and we're going to open the test for that, and we're going to want to activate the user. Okay? And let's see, our block tests Let's see. Okay, these are going to do a couple things. First, we're going to just try to mine a block. So the output of this should be basically a file on my desktop that is going to be a block that has all of the headers that we want and hello world at the end. Or, well, that's the unsuccessful one. Here's the successful one. Okay. I'm not using a previous block right now. That's one of the things we have to pass in. I'm not dealing with that just yet. Okay. So it's going to try and mine something, and then we are going to actually mine something again. And once we mine it, we are going to actually validate it as if we were getting it from a third party. So you can kind of think about, in order to, not that function. Really what we're interested in this test successful validate is loading the block and, well, I suppose. No, okay, so we're going to create a new block just for the sake of it, and then we're going to load that block into a data structure that we can read, and we are going to validate it. And this is just going to make sure that everything works. We can extract all the fields and all of that. And then this last one, test deconstruct block, again, we create a third block, but then I am manually stripping out all of the components. So I take out the key, I take out the lock, and I take out the data. And the reason for this is just to test to make sure everything works. So I can go into OpenSSL and actually use the key and the lock and data to validate the signature. So I want it to be, I don't want it to only work within the blockchain. The idea here is that you can take the bytes that are in the block file, and so long as you know what this structure is, you can extract those raw bytes and use something like OpenSSL, and it just is, it's as valid there as it is anywhere else. Okay, so it doesn't rely on any magic on my end to work. This is just the fundamentals of how these algorithms work allow this to be the case. Okay, so it's rather than me just kind of dictating that we have this user named Eric is me and here's his password, we have a way of actually kind of in a more fundamental way establishing the integrity of these things. Okay, so let's run our tests without further ado. I'm going to allow it. Oh, I don't want 100% success. Got a bunch of files on the desktop now. These are my raw block files. And what I really like about them is that I love the names of them. Let's first actually just use ls. First thing you'll notice, so that is the hash of our entire block. And what you can see is it starts with 0. So hello world is 12 bytes and the headers are about 1,250 bytes. So the difficulty here was really small, and we can tell that it worked because all 3 blocks start with a 0. So it is smaller than the largest possible by a significant amount. Plus, the hashes that you see here, if I hash this block using SHA-SUM, you can see that I get exactly the same hash as an output. Actually, it's slightly different because it cut off some of the leading zeros. I need to look into why that is. I don't want it to cut off leading zeros. So anyway, we can see that the hash of this as a file is actually the name of the file. That's why I don't embed in the block structure. Where is it? Right here. I don't actually have the hash of the block in the block itself, because that would change the hash of the block. And I want you to be able to hash this block and see that it is, in fact, who it says it is. So yeah, so the name of the file is just the hash of the block, and the hash of the block is not saved in the block itself. You determine it by hashing the block, and if it doesn't satisfy the difficulty requirement, doesn't matter what's contained in it. We're not going to accept it. Okay. Now, let's run a little test here. So we have data, we have sign, and what else did I extract? What I want to do is run this deconstruct block thing. To the test. Test block. There it is. Okay. Public key, sign, and data. So what I want to do is validate the data using the public key and sign. So OpenSSL DGST dash verify public key dot. Is it public key dot anything? No dots. Public key, and signature is sign. Is that correct? Yes. And I want to do it on data. Unable to load key file. Because I need to specify key form DER. Ooh, it didn't work. Okay, why didn't it work? I think I forgot to specify the algorithm. Hey, there it goes. Okay, so what we can see is that once I take all of the constituent elements of the block and I extract it into a sign, the data, and the public key, anybody can come and verify that this data was created by whoever owned this public key's private key. Okay, so we can guarantee the authorship of this data. We can guarantee the integrity of the data through the hashes. And we can guarantee that the person creating it has done the necessary work to make it a legitimate part of our chain. Okay, so that is kind of all of these aspects kind of playing together in a pretty complex way in order to create our blocks. So let's talk about where we are now with this project and what needs to happen next. So what we have here is the ability to create our blocks. Oh, well, before we go any further, actually, before we jump into what comes next, I want to point out another little thing of this blockchain. I have decided that all blocks are going to use this timestamp. It's going to be UTC time. So there's going to be no time zones on the blockchain. Everybody's using UTC time, and there's also no daylight savings. So that's just a fun quirk of the blockchain. Anyway, what's going to come next? So we have the ability to create these blocks, but I have nothing right now that can get these blocks again. So we don't have anything that can retrieve them, and we don't have anything that can share them on the network. So right now I can create a block on my computer, and I mean, I guess I can email it to you if you want, but that seems kind of lame. So we're going to need to create the server architecture for sharing blocks. And what I'm thinking is that we'll do this through a series of interfaces. These files down here, we'll have an author, a publisher, whatever we want to call them. And we need a module that is going to be responsible for retrieving blocks and sharing blocks on the network. So that's what's going to come next. And what I'm having difficulty with is in the consideration of this main file and how this is going to work when a single person is using it. So if we think about Apache for web hosting, you sort of turn it on, you leave it on, and it just runs. You don't interact with it. As opposed to OpenSSL, which you will run one command at a time, and that's it. Okay, what we need is something that kind of does both. So we need a server that is going to be running, constantly willing to accept and share blocks. But we also need a client that can run a single command and share something on the blockchain or create something for the blockchain. So exactly what that workflow looks like here, I don't really know. So that is a question for the future, and I am open to suggestions there. There's a link to our Discord in the chat or in the description, and if you'd like to jump over there and discuss how we can develop this further and design how we interface with it, then I'd love to see what your input is. And the same thing over on GitHub. We have a lot of, it's all open source stuff, so you're free to take a look at it. You can clone it, you can change things, you can open issues. I will often open issues and just have different things that people can work on if they want to contribute. We have a few people that actually are doing that right now. So we'd love to have you join us over on Discord and on GitHub. And I think that will do it for today. If you guys have any questions for me about any of this stuff, you can leave it in the comments. I'm not seeing anything in the chat. There was quite a lot here. I know that OpenSSL it's quite a thing. It's really, really powerful, but it deals with some very dense content, and the library itself doesn't really do you any favors in making it clearer what's going on. So I hope this is somehow helpful in whatever you are trying to use OpenSSL for, and maybe I've piqued your interest in my project here, so feel free to join us in contributing there. So hope you've enjoyed this, and I will see you next time. Toodaloo.